technology as well as just transportational industry knowledge. So an overview on what we're doing, we're essentially creating a bi-computational network management system of which we can really control braking, propulsion, as well as electrical data transmission, and essentially learn how Hyperloop pod goes back and forth and actually moves and fail-safe design. So we utilize processing equipment such as microcontrollers, Arduinos, various sensors, motors as output mechanisms, as well as feedback loops for error correction.
So this year the power team worked on creating a battery eliminating circuit using various voltage regulators. The main goal of all of these circuits was to sustain the Raspberry Pi's constantly changing current as well as make it run consistently. Shown here is a circuit using an LM7805 voltage regulator allowing for adjustable voltage output, and the main goal of this one was its ability to protect the Raspberry Pi as well as power it up to a 35 volt input and still protect from any current spikes coming from the battery.
So for my part, I worked on a circuit using an LM317 voltage regulator. And the nice thing about this 317 is that it's an adjustable voltage regulator, meaning we can adjust the output voltage slightly by simply changing some of the resistor values in our circuit. One of the big challenges we came into with these circuits is have a reliable reading of output current and voltage, hence the use of a big 5 watts approved shunt resistor at the end, which is only a 2 ohm resistor, so that we can have a steady reading of that current output. And so upon testing and theoretical data, we initially found that the data was reliable for our requirements, but when testing with the pod, we figured out that this circuit was not able to sustain the changes of the Raspberry Pi due to its connection to the internet, so changing voltage and currents. So.
This past year, I have been tasked with keeping the CPP Hyperloop pod safe by ensuring that both the input and outgoing power is regulated at all times. In order to keep the pod running smoothly, I designed a battery emitting circuit using a buck converter, which takes in power from the battery and reduces the voltage to fit the specifications of the components. In the lab, I successfully tested the circuit with an input voltage as high as 23.5 volts, and the output voltage remained a steady 5 volts. However, upon connecting it to the Raspberry Pi, the circuit struggled to retain its voltage due to a high voltage drop in complex power. Voltage regulation is a requirement for all power systems because each hardware component is unique and contains its own power specifications.
This year, I was responsible for setting up and analyzing temperature sensors on our pod components, so if they overheat, we can immediately implement safety procedures that stop the pod. I tested the accuracy of temperature sensors by starting at room temperature and then putting them in boiling water, since boiling water is always 100 degrees Celsius. And I also measured the time that elapsed while the sensors max temperature. Even though the sensors are all the same model, each sensor performs slightly differently, and there can be a significant time lapse between when the data needs to be collected and when the sensor starts picking it up. And to be able to stop that one at a time, it's really important to know that there's a delay between when a signal is heard in the pod and when a sensor picks up on it. And you have to be able to identify what that delay is and digital code and the sensor plane to account for it. And you can see the sensors right here. Since we need to understand the environment that we are working in, we also implemented a sensor that detects the atmospheric pressure around the pod as well as the altitude and the temperature. To test the sensor, we used a can of pressurized nitrogen spray in order to deliver controlled bursts of pressure to the sensor. From these tests, we found that as temperature decreases, pressure increases, and this helps us better theorize the operating specs of our pod's brakes and motors.
Using a voltage divider, we're able to know the battery's capacity in the Hyperloop pod. For my data study, I used an Arduino Pro Micro to determine the amount of voltage left in a 9-volt battery, with the OLED screen displaying how much voltage. 9 volts goes into the Arduino, 5 volts goes into the OLED, and the voltage divider probes the 9-volt battery. For general uses in electronics like smartphones and vehicles, this can be used to consider how much voltage is in the system. For the purposes of the Hyperloop pod, this project tells us the threshold for when thinking about a fail-safe for a scale-up version.
a number of sensors were investigated for determining velocity and acceleration of the pod itself. And in a theoretical Hyperloop situation, the pressure and temperatures and vibration and many things cause a lot of issues. And so a visually based system was decided to determine position and velocity. And the first figure shows an example pattern of stripes that are placed within the tunnel, or in our case on our track, to determine position and therefore a rough velocity. And we also use an IMU to buffer that information, to accompany that information. And presented to us was the BNO 055, and on paper it seemed like a golden solution because it presented already calculated values with a coprocessor, and we came across a number of issues regarding timing and the embedded firmware in that sensor, so we are investigating other options for that. The Bosch BNO 55 does, however, come with very good uses for fault detection, sudden losses of acceleration, poor orientation, and the like.
So live vision on board the pod provides a wealth of information, but with the wealth of information comes a wealth of data that needs to be transmitted. Using the network infrastructure that we've been using for the rest of our data, best case scenario network situation, we were seeing maybe between 1 and 5 frames per second of video, and just ridiculous latency. But using FFmpeg and an RTMP server on the same DPS that we're using otherwise, which is the same technology that like YouTube live streaming uses, we're seeing look how fantastic that looks, look how smooth that looks. 30 frames per second, 40p video, not terrible compression.
Yeah, so in order to create the next proposed high-speed transportation system, we have to look at something that's practical and implement. So in our club, we decided to create 2 custom PCBs, which is a printed circuit board. The first printed circuit board is an electronic architecture circuit, which encapsulates all the microcontrollers, included sensors, everything onto one platform. The second PCB we created was a voltage regulator circuit, and essentially this helps us optimize on the efficiency of our electronics as well as mitigate parasitic properties, because the other substitution is a conventional method of a breadboard, and it's just faster to really create the PCB and fabricate it in-house or out-house.
So we have a lot of data and sensors coming from the pod, but how do we actually see that when the pod's moving really, really fast? Well, in this case, we would use networking coming from the Raspberry Pi. The Raspberry Pi connects to the internet, which sends our data off to a wireless server, and then we can access that wireless server for data. That's pretty much the simplest way it works. We also have a graphical user interface, which will be presented later, where we can actually read the data and then actually control the pod. So there's a 2-way communication protocol being used here. The latency in this system is around 20 milliseconds, which is really great for ping-wise, and we can even decrease that if we test the pod locally. This was developed during quarantine, so a lot of what happened here was we were trying to allow more members to access the pod from home, so people would actually be able to press start on the pod and have the pod moving over like a distance of like 1 to 2 miles, and it would still be functional.
We are also holding workshops for engineers and non-engineers alike. And here is the schedule. It has size 12 for your new font, and you have to scroll down. Well, don't worry, I redesigned it so that it is all on one page. The font is now modernized and more readable, and it now has color. And this is good because it broadens our communication to the public, which is good since we have a lot of events and information we just want to put out. And this is our website. It has the list of members. We have the workshop schedules on there as well, and it also holds our progress for this semester and the future semesters.
So throughout the last year, we've learned a combination of hard and soft skills. Some of these hard skills include using GitHub on large-scale projects. We've troubleshooted a control system, more specifically with the IMU. We've attended workshops such as soldering, Arduino, PCB design. We've also had workshops on Python and some mechanical engineering ones as well. And throughout those workshops, we've also learned some soft skills, such as how to communicate with a team effectively. We've held productive meetings. We've learned how to work with an interdisciplinary team, because we have a bunch of different types of engineers working on our team. And we've also had a specific workshop, like specifically geared towards troubleshooting certain problems and how to fix those problems. And because of all this, this controls this pod.
But yeah, so generally what CPP Hyperloop is all about, it's not just the technical aspects. We have civil engineers, we have BCD majors. It's a full encapsulation of an interdisciplinary team, and on top of that, it's just figuring out how do we become principled engineers in the workplace as well as principled business leaders. So, do you guys have any questions?
It sounded like you tried 2 different kinds of regulators, and none of them were able to control or keep the voltage constant for the Raspberry Pi?
No. We have three types of
Okay.
regulators.
What was the one that worked?
The one with the 7805 that Alex presented at first is the one that we went with at the end, because that's the one that sustained the changes of the Raspberry Pi.
Okay, and that's a 3-terminal regulator?
Sorry?
Right, it's got an input and output? And
Yes,
output?
absolutely.
Okay.
Yeah.
How much power is it dissipating?
I could show you with the 317. We were definitely having more. We did have a 1.5 amp output, and so that's why we use the 5 watt 5 watt approved resistor, because it was inputting a lot more. I couldn't tell you the exact value.
Okay, and then the next question is, has anybody done the calculations of how big of a heat sink you're going to need to keep the thermal junction temperature where it needs to be?
Pretty sure that's the next step.
Yep.
Yeah.
Because otherwise they'll just go poof.
Yeah. That's what we found. But we were just using regular shunt resistors, and they were just going away, burning instantly. So that's why we wanted to get a steady reading first, and now we're gonna
Just get a big chunk of aluminum and screw it onto it.
Yeah, for sure.
And I can say something about this as well. The Raspberry Pi at its peak, the reason we were so concerned about this is because all our sensors and everything were controlled by this one big battery, which was also used to power our motors. So we needed this BEC, the battery eliminating circuit, to separate these two systems. The Raspberry Pi at its max current draws about 3 amps when it's connected to the Wi-Fi, but then stabilizes around 1.5 amps. So when the power team did their test, they did a retention test and an activation test. The retention test, where we powered the Raspberry Pi with a power source that we know that works, and then tried to plug their circuit in to feedback power, and then yank the main power supply out. So if their circuit could keep the Raspberry Pi alive, which means that it feeds them enough current, or the Raspberry Pi is able to draw enough current from the system, then they pass the retention test. But also we need the activation test. So when they plug in their circuit into the Raspberry Pi, it's able to do its full boot process, draw 3 amps, stabilize down to 1.5, and then there was a slide in which we were able to ping Google. So that was pretty much our solution to the experiments.
Any more questions from the audiences? I have a quick question. How can you guys manage such a big team and organize a presentation within 12 minutes?
Yeah, a little chaotic, but I mean, we're all kind of leaders of our own ends in the sub-team, so I think it was very efficient in organizing.
We have good leaders.
How many times you will rehearse before the presentation?
I don't want to know. A better answer.
We've been rehearsing this presentation since the beginning of the month, because I wanted to give our whole team a chance to present to an audience and answer questions like this. It's a really good way of developing their soft skills. So each meeting we would take some time to just go through each person's speech and have them pinpoint down to the core details of what they're doing.
Yes, thank you very much, and very well prepared presentation.